Right, hello, my name is Ming, and I'm going to be talking to you today about Adelic geometry via topos theory. And all this is joint work with my supervisor, my PhD supervisor, Steven Vickers. All right, so let's go. So, okay, on this slide, we have a program for the talk, and I'm going to be discussing two basic themes. So the first theme is, in what sense can we consider growth-induced toposes as generalized spaces? And the second question and second theme is, when can we solve a problem by breaking it up into smaller pieces? And these two themes will sort of inform the content of this talk, and will sort of, well, what I hope to convince people is that this program of Adelic geometry via topos theory serves as an interesting test problem for sort of illuminating how these two themes might interrelate with one another. Okay, so let's say something about how growth-induced toposes can be viewed as generalized spaces. So in classical mathematics, like a lot of our language and our concepts are cast in terms of set theory. And in the context of point set topology, what we have is, right, so what is a topological space? Well, a topological space is a set whose points are elements of that set. And it also comes equipped with some additional structure known as topology, right? The set of opens has to satisfy certain kinds of nice properties. And additionally, we also have a notion of a continuous map, which is in some sense a structure preserving map between the two topological spaces. And well, structure preserving in the sense that the pre-image of the continuous function preserves opens from the codomain. And so that's the classic point set topology view. So in the context of point-free topology, what we're really doing is pulling these topological ideas away from the set theory into a more general context. And it is in this sense we start to give substance to how toposes can be viewed as generalized spaces. So, okay, what is the analog of point here? Well, we have a notion, the notion of point here is that they're no longer elements of set, but now they're models of a geometric theory. And I'll say a little bit about what that means on the next slide. And we also have a notion of space. And now the space will be, right, the world in which the point lives, in which the point in this point-free sense lives with other points. In other words, the growth-induced topos. And we also have a notion of a continuous map. In this particular case, it will be a geometric morphism that, again, is in some suitable sense a structure-preserving map between two generalized spaces. I think I will not be, because this is just a short talk, I will not be going to into the finer details, but I do hope to give a sense of like what these concepts are, even if we have to sort of, well, black box or gray box some of these ideas. So in particular, I would like to focus on like just bring out a couple of points about the point and space in the point-free sense, so we have a bit more intuition about what that means. So, okay, what is the geometric theory and what is a model? So a theory is some kind of syntactic description or formal description of mathematical structure, and a model is an object that satisfies this particular structure. So the purpose of this slide is to just give you an example of what that means. So we have a theory, right, of Dedekind reals. So a Dedekind real number, well, a real number can be understood as, you know, comprising both a left and a right Dedekind section, which in essence are two subsets of the rationals possessing certain kinds of nice properties. And these nice properties can be axiomatized using geometric logic, right? Geometric logic, just think of it as just a particular logical description that adheres to very specific rules. And what it's just saying, what this slide is saying is that these rules are sufficiently rich and sufficiently expressive for us to capture and express this particular, to express what the suitable description of Dedekind reals are. So that's the geometric theory side. And the model of this particular geometric theory is, well, a Dedekind real, right? And so, right. So in other words, it will be a pair of Dedekind sections, a pair of rationals, a pair of subsets of rationals possessing the required properties. All right. And what about the notion of a space? So if some of you are familiar with the notion of the growth-induced topos, you might be aware that it classically is defined as, you know, a category that's equivalent to some some category of sheaves constructed over a growth-induced site. What this slide is trying to indicate here is that there's another way of trying to understand what a growth-induced topos is. A growth-induced topos can be understood as a classifying topos of a geometric theory. In fact, all kinds of growth-induced toposes are classifying toposes of geometric theories in some sense. And also all geometric theories possess and can be canonically associated to a growth-induced topos as well. We'll sweep the details under the rug, but really the upshot that I want to say here is that this really gives substance to the slogan of how we can view points of the topos of this generalized space as models. In particular, it gives us a way of thinking of doing category theory, a very interesting way of doing category theory without reference to objects, right? In category theory, we often talk about, objects or morphisms between objects and all the kind of nice categorical properties that this category must have in order for us to perform certain kinds of constructions. What this is saying is that, well, we not only can reason in terms of the objects of the topos, we can also reason in terms of the structures that this topos classifies. So we have an interesting dual perspective here between the objects of the topos, i.e. the sheaves of the topos, or the points of the topos, in other words, the models of the geometric theory classified by the topos. And additionally, we don't just have models of a geometric theory, we also have the notion of a generic model. And very simply, this just is saying that there's some special model that lives within the classifying topos of the growth index topos that allows that freely generates all the other models of the theory. So in other words, if you have a theory, or if you have a theory and you have a model, there's a generic model. Well, there's a way of cooking up, loosely speaking, this particular model from the generic model. And so this is sort of illustrated by this picture here. Like you have a generic model indicated by this yellow diamond. And that's the generic model, and all these other shapes are the models of the theory that's been cooked up from this from this generic model. So, okay, we have this notion of a generalized space, we have the notion of a generic point, and we have a notion of, some sense of how this dictionary between point set and point free topology works. Now we turn to the other side of the story, which is the Adelic geometry side. So, all right, there's a thing that we do in mathematics a great deal where we have a problem and it's really, really hard to solve. And what we do is we break the problem into many different pieces. We solve the problem for each of the smaller pieces and we put everything back together again. And this is a very interesting incarnation in the context of number theory or Diophantine geometry. So here's a polynomial, right? A perfectly respectable polynomial. And we can ask a very basic question, like what are the rational or integer solutions to this polynomial? In other words, are there like rationals x, y, and z that we can plug into this polynomial such that, raising it to the appropriate power, we get 0. And this question is very simply stated, but like in general, like it's really hard to solve this particular to get an answer to this question. But there are a couple of key observations that we can make that sort of indicate a promising line of attack that makes the problem a bit more tractable. So the first observation is that integer solutions or rational solutions imply real and mod p solutions. In fact, mod p solutions, right? So integer solutions obviously are real, and mod p as well. And also the second observation is that real and p-adic solutions are often easier to deal with than just integer and rational solutions. And this can be viewed as some statement about how in the context of the reals and in the context of the p-adics, you do have a richer geometry to work with as compared to the integers and the rationals. So there's more structure for you to exploit in order to get specific results. So combining these two observations together, we can form the converse question. So suppose we have a polynomial with rational coefficients. Does knowledge about its p-adic and its real solutions give us information about the rational solution? So we're moving in the opposite direction. We know that rational solutions imply p-adic and real, but does the converse apply? And this sort of gives rise to, is a starting point for Hasse's local global principle, which very roughly speaking says that something is true for the rationals if and only if it's true for all the completions of the rationals. And this principle does not always hold. There are polynomials where you do have solutions for all the p-adic and the real solutions, but you don't have a rational solution. So it's quite a subtle question, but it's also helpful to try and understand what exactly is going on the level of completion. So it'll be helpful to have some sort of device that allows us to reason about what is true or what holds for all the completions of Q. And this is where the Darwin comes in, right? I'm going to slide over the technical definition, but morally you should just view it as a device that allows us to reason about all the properties of the completion simultaneously. And all right, on the first slide, we presented a dictionary between point set and point free topology. And we made a comment about how we were pulling topological ideas away from set theory and reformulating in the context of point free topology. And this was allowed for by the language of topos theory. And a similar move can be performed here when we can ask the question, instead of asking whether a property holds simultaneously for all completions of Q, right? We can also ask if a property holds for the generic completion of Q. And if this is a good and meaningful reformulation, then this means that this opens up a lot of questions from number theory to the methods of geometric logic and topos theory. And so this forms the interesting starting point of our investigation of this research program, Adelic geometry via topos theory. We're trying to reformulate a lot of these ideas in the context of geometric logic and classifying toposes. And so, okay, on the previous slide, I said something about completions of Q, but let me just say a little bit more detail, what we mean by this. So, all right, what is a completion? Well, in order to have a completion, we need to sort of fill in points, right, with respect to some sort of distance metric. And this is given by the absolute value. And an absolute value is basically a function from Q to R that satisfies these very reasonable properties of a distance function, right? Things like multiplicativity and the triangle inequality, like reasonable things you would expect if one has passing acquaintance with the theory of metric spaces. But additionally, we don't just want all completions, but we want all completions up to isomorphism. So, there's certain kinds of completions of Q which are sort of topologically isomorphic, and we want to sort of say that, well, they're essentially the same from the point of view of the Hasse local global principle. So what we want to do is we want to factor out, or we want to quotient by a particular equivalence relation. And well, okay, this is the purpose of this. Well, this is what we're saying here on this slide, that a place is an equivalence class of absolute values. If given two absolute values, there exists some alpha in this particular interval such that you can raise one of those absolute values to the power of alpha, and this is equivalent to the other one. And as it turns out, this particular formulation coincides with, if two absolute values belong to the same place, then they give rise to topologically equivalent completions of Q. And so, okay, so what we would like to do as a first step towards constructing the generic completion is to have a notion of what the generic place looks like. What does the generic equivalence class of these places look like? And so there's some basic properties that we would expect this equivalence relation to sort of impose on the space of absolute values, right? So okay, suppose you have a space of absolute values and you have this sort of action that's being induced by the exponentiation. So right, what would the points of the classifying topos of places look like? Well, as stated on the previous slide, if you raise one to the power of alpha, this should be equivalent, right, to the original thing. We also want to say that if you raise it to the power of 1, you get back exactly the absolute value itself. And also there's some sort of associativity property here. So that means if you raise an absolute value to the power of alpha and you raise it again to the power of beta, then it's this equivalent to raising this absolute value to the power of alpha times beta. So like very reasonable properties. But what is really the upshot of this is that really there's some sort of we would like to, right, taking the point of view that the models of, all right, so previously I sort of glided over this, but like these are some properties that we expect an absolute value to have, and these can be encoded, just take them in faith for now, can be encoded using geometric logic. We know that geometric theories are can be canonically associated to some growth-indeed topos, which means that there's some sort of generalized space of absolute values. And what is the classifying topos of places is that it's this generalized space of absolute values quotiented by some sort of algebraic action. Sort of two questions here. So, all right, is this notion of real exponentiation geometric? Like, does this notion of raising an absolute value to the power of alpha make sense in some sort of geometric terms? And to that question, the answer is yes. And there's a preprint on the archive between myself and Vickers. There's sort of details of point-free construction of real exponentiation. And then the second question, which is a very subtle and interesting question, which is, it asks, well, what exactly does it mean to quotient by an algebraic action? In particular, is there a difference between quotienting by a monoid action versus a group action? And this is where interesting subtleties between, subtleties in the relationship between topology and algebra start to emerge. So as it turns out in our investigations, when it comes to the p-adic places, the quotienting is in a group action. And therefore, the resulting quotient space is a point. So each p-adic place or non-Archimedean place can be associated to some honest point. Whereas on the other hand, the Euclidean absolute value or the Euclidean place is quotiented by monoid action. And so the resulting quotient space is not a point. In fact, there's some sort of weird blurring going on. So this is sort of a candidate picture about the situation. So on top you have the p-adic absolute values, each associated, the p-adic places, each associated to some prime of the integers. And below you have the blurring going on, the interval that's associated to the Euclidean place. And so, all right, so this is, right, that's what the block is saying, that basically the point, the Archimedean place is not a point, but rather it's some sort of blurred interval. And this is really interesting because, like, if we just sort of reflect this back into like classic mathematics and classic number theory, like Arakelov geometry is sort of guided by this fundamental tenet of this analogy between the point at infinity of the projective line and the Archimedean place. And so that sort of leads us to think that, you know what, we have all these different points corresponding to the non-Archimedean places, and what the Archimedean place is, or what the Euclidean place is that it's basically the additional point at infinity. But what this picture sort of shows is that really thinking about this as a point, the Archimedean or the Euclidean place as a point really starts to raise certain questions. There's some indications that it really isn't a point. And so, right, our candidate picture suggests that there's some sort of interesting blurring going on. So point at infinity is not just a classical point with no intrinsic structure. There's actually something more subtle going on there. So, all right, let me just conclude. So what have I said to you? I've sort of introduced two themes, right? The first theme is viewing toposes as a framework, uniting logic and topology, gives some sense as to how we can view toposes as generalized spaces. And the second theme is like these local global issues, right? Breaking up problems into smaller pieces and investigating how we can put things back together again. And through this notion of the generic model, the generic point, this sort of gives us a way to like connect these two things with one another. And one interesting upshot is that like pulling away from the set theory sort of reveals key insights into this deep nerve connecting topology and algebra. And in the final few slides, what sort of briefly indicated was that, you know, there's some evidence that there's some very interesting blurring going on at infinity. So Spec Z is just basically this particular, well, this space that's traditionally viewed as, well, some sort of one-point compactification. And what our picture indicates is that, well, the additional point at infinity, or the additional Archimedean place, isn't really just a point. There's some kind of interesting blurring going on, and it'll be interesting to explore the precise implications of this. And all right, so that's all I have. So yeah, thank you very much.